as a very important example for complex semisimple Lie algebras, we'll talk about SLNC. Consider the complex Lie algebra G equal to SLNC. By definition, this is a collection of n by n matrices. Remember, the set theoretical structure of GLNC is just n by n matrices over C. But additionally, there's a Lie bracket defined on this space. SLNC consists of the matrices in here, satisfying that the trace is always 0. And here, in case you don't remember, let me remind you that GL in C as a set is equal to the n by n matrices over C equipped with the Lie bracket defined by Lie bracket of A and B is equal to AB minus BA, where the multiplications here are just matrix multiplications. And now let us introduce some Lie subalgebras of G. First, let H denote the Lie subalgebra of G consisting of diagonal matrices. And let H0 denote the Lie subalgebra of all real diagonal matrices in G. Namely, every matrix in H0 has only real entries. Then, if you regard this H here as a real Lie algebra, then H is equal to, or rather isomorphic to, H0 direct sum I times H0, which, by some classical terminologies in Lie theory, this can also be called the realization of the complexification of H0. However, mathematicians are lazy, so by convention, this complicated notation can also be simplified to just H0's complexification. As long as it is well understood that we are studying those stuff as real Lie algebras. If you want to know more information about this realization of complexification, I would suggest you to read Knapp's Lie Groups Beyond the Introduction, 2nd edition, page 34 at the bottom, where you can find more stories about this. But at this point, let us not worry about this too much. Okay, now, let us continue with more notations. Let E sub ij be the matrix where the ijth entry is equal to 1, where all the other entries are equal to 0. This is an n by n matrix, and henceforth we'll be mainly interested in such matrices where I is not equal to j. And we define a member E sub j of the dual space H star of H by E sub j applied to the diagonal matrix H1 through Hn in H being equal to H sub j. Namely, E sub j will subtract the value of the jth component on this diagonal. It should be hard for us to see that this is a linear functional on H. And now we will make the following claim. We claim that for each H in the Lie algebra H, the adjoint operator ADH is diagonalized by the basis of G consisting of members of H and those E sub ij's where I not equal to j. Now let us verify this claim. Indeed, we have that ADH applied to E sub ij by definition is this Lie bracket of H and E sub ij. And this, the definition of this Lie bracket is H times E sub ij minus E sub ij times H. And this guy, this first thing, will be the ith component of this diagonal matrix times Eij, while the second guy will be the jth component of H times E sub ij by simple linear algebra matrix multiplications. And using the terminology we just introduced, this y will be equal to E sub I of H minus E sub j of H times E sub ij. Namely, E sub I of H minus E sub j of H is an eigenvalue for this adjoint operator with eigenvectors E sub ij. And for H prime in H, what is ADH applied to H prime? This guy will be equal to, by definition, the Lie bracket of H and H prime, which is HH prime minus H prime H. But this H and H prime are diagonal matrices, so they commute with each other, which means this guy will be equal to 0. So trivially, this H prime is an eigenvector for ADH with eigenvalue 0. And it should be easy for us to see that those E sub ij's with I not equal to j and those matrices in H will form a basis for this Lie algebra G equal to SLNC. And if you want to be more specific, you might want to choose those members of H to be E sub 1 minus E sub jj, where j is greater or equal to 2, less than or equal to n. So that from linear algebra you will see those guys and E sub ij's are really linearly independent, and they will span this G equal to SLNC. And the reason that I chose E sub 1 minus E sub jj is that because I'll always need the traces of those matrices to be always equal to 0, as per the definition for SLNC. This finishes the verification of this claim. And from here, we're going to introduce a new terminology concerning E sub I minus E sub j. As I mentioned earlier, E sub ij is a simultaneous eigenvector for all ADH, where H is in this Lie subalgebra H, with eigenvalue E sub I of H minus E sub j of H, which is E sub I minus E sub j of H. Now you can see the special role that E sub I minus E sub j is playing in here as a linear functional on H. And later on we will call that E sub I minus E sub j a root for I not equal to j. And the set of all roots will be denoted by delta. An important remark to make here is that roots are linear functionals instead of scalars. And the reason that we are introducing roots is the following theorem, called the root space decomposition for SLNC, which states that for G equal to SLNC and H is the Lie subalgebra of G consisting of all diagonal matrices, we have the following decomposition of Lie algebra G. G is a direct sum of H with a direct sum over all pairs I not equal to j of the one-dimensional complex linear space spanned by E sub ij's. And this can also be written as G equal to the direct sum of H with the direct sum over I not equal to j of G sub EI minus EJ, where G sub EI minus EJ is equal to the simultaneous eigenspace of this adjoint representation with respect to EI minus EJ. And this theorem is a core part for this motivating example, SLNC.